and starts recording then.
Wow.
Yeah. But it's nice because it does things that I sometimes forget, like turn on the microphone and stuff like this, and then it will save the video automatically at the end, convert it to MP4 so I can upload it. And yeah, thank you for your sarcasm.
No, it's actually cool. Yeah.
Then add this little feature in.
Is that like basic program?
So I could have like a little square of me as I'm editing. Okay. So if I ever need to emphasize something in the video, I can open up the box and go, this is really important. Okay, so this is the last book for this semester, and then we'll have a look at exams. So we're going to finish with this semester with waves. Okay, so if we can go to the first page then, please. Waves. Okay, so here there are two types of waves. Joshua, where is your notebook? Are you planning on not writing? So there are two types of waves, and I'll start by saying that both these definitions could be in the exam. So they could ask you these definitions in the exam. Okay, so first wave oh yeah, you told me to be like, come on in.
Why are you so happy?
Well, I'm laughing, what's happening?
So firstly, before I define the different types of waves, I should define exactly what a wave is. Okay. Now this definition is, I'm trying to make it as simple as I can, but it's kind of difficult to define something that is simple because we all have an idea of what a wave is. Like we can picture a wave, but how to define a wave? So the simplest one I can come up with here is a disturbance moving from a source to the surroundings, and I maybe should put this in brackets, and this causes energy transfer or energy to transfer. It's the simplest I can make it. So the wave, firstly what a disturbance means is really just, the other way I think about it is vibrations. So disturbance means vibrations. So a wave is a disturbance moving out from a source into the surroundings. And this causes energy to transfer. So if you think about it, here we have energy. What type of energy is this shaking? Kinetic, isn't it? So if it moves out here, the kinetic energy is moving out as well, okay? So this is the minimum, simplest definition we can have for a wave. A disturbance that just moves from a source to the surroundings, and most importantly, it transfers energy from the source to the surroundings. So, for example, sound wave, as I'm speaking, there's sound energy moving out, okay? Light energy as well. Yeah. What are you saying?
Does it stay in kinetic energy as it transfers?
No, actually, no. It could change its form. Yeah. So, like, for example, the light energy, I mean, it's light until maybe it hits something and warms it up, and then it's heat energy, you know. Same goes for sound as well. I think you could probably warm something up if you put enough sound onto it. I'm not sure. I would need a whole lot. But no, it could change its form. Okay, so that's wave. And then I said there are two types of waves. So that's what we're going to do now, yeah? I don't need the Wi-Fi, it's okay. But I'll close it now. There are two types of waves, that's what we'll do next. Yes. Sorry. Okay, do you have this written down? Yeah? Yeah, okay, so first wave we'll do, yeah.
Look at yourself then, and then judge others.
What's wrong, Tom?
Nothing.
No, really, what's wrong? Try. Please remember I'm sick, so please be kind. Transverse wave is the first type. And there's a nice picture there of a transverse wave. But a transverse wave is the simple one that you picture, you know, when you go to the beach, you look at the ocean. It's the one that you draw. If I said draw a wave, you would draw something like this. Like the sine or cosine. So what's happening is the motion is, it could be up and down like this, and also maybe moving in that direction. So it's, you know, it's hard for me to draw, but if you picture an ocean wave, it's going up and down, isn't it? But then it's also moving towards the coast. Yes, and we could have keywords here. Like the vibration here is perpendicular to the direction of movement. I mean, these two here are perpendicular. Depends which way you want to describe it. Okay?
How would you...
So I thought it was parallel.
What is... Well, parallel is just a word. What is parallel to what?
I thought it was parallel to the source of vibration. Or
That is the other way.
That's longitude.
Well, we have the other type to look at that vibrates like this as it moves out. Is that what you're thinking of?
Yeah.
I don't think they necessarily use the word parallel here.
What is the...
Perpendicular.
No, they use perpendicular.
What
Yeah.
is the definition of transverse wave?
Yeah, so I would put transverse wave down as the vibration is perpendicular to the
Direction of movement.
but there's a special word for that direction of movement.
Propagation.
Very good, propagation. So we can say that, now you don't need to use propagation in the exam. Direction of movement is fine. So we can say that the vibration of the wave is perpendicular to the direction of movement. Or maybe even to be more technical, direction of energy transfer, because the wave, if it's moving that way, is sending energy that way.
So which one is perpendicular to its...
Yeah, so we can say the wave vibrates, I'll emphasize this, perpendicular to the direction of movement. And as you said, Tanish, another word for direction of movement is propagation. Or as I said, another way for saying direction of movement is direction of energy transfer. So you have many choices, all are fine for the exam. This is the simplest one. Okay, can I do the next type now? Did you write that definition down?
Yep.
Yep, okay. You are writing this down, aren't you? Good, okay. I just had a moment of worry there. Right, next type. And again, there's a nice picture of it there on page 3. Okay. This one here is more difficult because it's more difficult to draw and you don't see it. So I'll try my best to draw the idea here. Okay, so the wave again is moving that way. but this time it's vibrating. Ooh, this is perfect. This gives me a chance to use my video. I can demonstrate it with my hand. Nobody has a spring by any chance, do they?
Not today, sorry.
Okay.
Actually, in the pen, someone might have it in the pen.
Yeah.
Oh no, we won't go to that level, it's okay. So here, what's happening is the wave is moving. Huh? I don't understand. If I just did this, it's not funny. But now because it's on the screen, now it is funny, yes? Alright. So first the non-screen version, and then the screen version. So what's happening is the wave is moving back and forth as it moves towards the wall here, okay? So the transverse wave will be going up and down, up and down, up and down as it goes to the wall, okay? And then this wave is vibrating back and forth. So that's the parallel one. All right, we'll try and demonstrate this now. Hang on, I need to. All right, like so.
That's the parallel one.
Yes. I realised actually this when I save this might not even show up when you're watching it at a slower frame rate. It might just be my hand moving across the screen. But you get the idea.
Yeah.
So now that we have the last definition, who wants to try and give me this definition? The same except
For parallel.
yeah, swap perpendicular for parallel. So you can start writing the definition. I'll write it here. Now, what did I say exactly? The wave. Yeah, okay. The wave vibrates parallel to the direction of movement. Can you have a look at the picture on page 3 actually? Because I think it does a good job there of showing you the two different types. So if you look at the top of page 3, they use a spring to show you the two types. So the first one, A, transverse wave, that's when you take your spring, look, and you snap it. And it sends a wave running through it going up and down. So you snap it, okay? Then the second one, B, also called longitudinal or compression wave, is when you take your spring and you push it like that, and it sends a pulse running through it. Yeah?
What about this thing with lots of poles? When you like take one, it hits others, and
Oh, that's
Newton's cradle.
Yeah.
How's that related to this?
I wanted to ask, is it somehow connected to the?
Oh!
Maybe.
Not quite that I can see. No, I think not. Well, it is an energy transfer, but if it was to be like a wave, it'd be like this one. That one hits the next and sends a kind of ripple through it. Be more like a standing wave, actually. We'll do that later, standing wave. Okay, so did you write this definition down? Now, I would like you to rewrite it fully. Just replace perpendicular with parallel. Have you done that? Yeah. Okay, so that's the different types of waves. So now we need a little bit of vocabulary to describe our waves. Okay. Actually, what I'll do is I'll draw you a beautiful wave here. And I'm going to just name the different parts of the wave. Some of these words you might already know. And in fact, you might know them just from maths class. So like the top of the wave is the maximum, but there's a special word for that.
Amplitude.
Not the amplitude. I'm talking about the actual point on the top that has a name. Crest.
Oh, crest.
Yeah, and then the lowest point?
Top.
Top, good, okay. And then what is amplitude then?
The distance between equilibrium to the top.
Yeah, not quite the, I think it's half the distance actually.
Yeah,
I
it's
think.
full distance.
Or is it the full distance?
No, from equilibrium to the top.
Yeah.
From the middle to the top.
The middle to the top, so it's half
Half of
the distance, yeah. And then the period,
This
or the wavelength.
from the
this is
same
one,
position.
one.
Yeah, like what we did in maths class, from start to end then. Okay. What's that?
One cycle.
One cycle, very good, yeah. Okay, so when my program's loading there, we'll draw the wave and we'll try to name all the parts. Oops. Okay. Oops, okay. Right. Let's see. Yes, so firstly, we'll do these in red. The whole length is called the wavelength. Wavelength. Yes, okay. And then here to here, that's called the amplitude. What else? We have crest and trough. Do they do that here? They do. Good. Okay. The top is called crest, and the bottom, which you all knew, is called trough. What else? Wavelength, crest.
Isn't
I think-
then somehow equal to
Oh yeah, we'll do the formulas now. I'm just trying to think. Is there any other names for any of the parts? Amplitude, trough, crest, trough, amplitude, wavelength. That's it, isn't it? That's all the formulas. Okay, so we can now put formulas together here. Oh yeah, the letters. What letters for amplitude? A. And then wavelength? Lambda. Okay. And then crest. Will we give that a letter? I don't know. If we just want to say max here, and then this one we'll just call this length here min. Okay, so a formula for amplitude, just like what we did in maths class. Yeah.
What about frequency?
Frequency. Yes. Now that comes into it when it actually starts moving. Yes. So we will get to that. A. What could be a formula for A?
1 over t.
Crest.
No.
No, looking at this.
Crest minus throw divided by 2.
Yeah. The maximum length minus the minimum. Well, if these are both positive numbers, they should be plus. But I'll just write as minus minimum over 2. But just be careful. What you really need on the top would be something like a number minus a negative number over 2. In other words, it's the whole length.
Oh, so it's
Divided by
maximum
2.
plus minimum in other.
It depends if you're using positive or negative to measure down. So I don't want to complicate things. I'll just make a note here that max is a positive number and min is a negative number. But of course, I mean, it doesn't have to be like this, but this is how I've drawn it. Okay. Oh yes, actually, here, if I call this, let me just call this small a, and I call this here small b, you know here to here is the wavelength, isn't it? But another way of getting the wavelength is you can say the wavelength is twice the distance from the max to the min. So the difference between, in this case, B and A, or A and B. Yeah, twice. So if you go from the max to the min, the highest to the lowest, double that number, you have one wavelength. You look very confused, Hanish.
No, is the B represents the longer one or just short from the middle to the end?
Oh yeah, okay. If this is like on an x-axis, here would be 0, here's A and here's B. So B will be to here, and A is to here. In other words, Tanish, I'm saying that the wavelength is twice, I don't know, we'll call this here, let's give it some letter, delta or something. Twice delta. Twice the distance between the max and the min. And if you remember, Again, I said something similar to that in maths class for our first graph question. That if we go from max to min, that's half of one cycle. I think it was 1A on the graph page. Ali meant brought it up or something, or you had some other way of doing it. Actually, I don't think you quite said that. Okay, have you all drawn that?
Yep.
Yeah. So now we can talk a little bit about what you were saying, Mohammed, about frequency. Okay. Can I scroll down? Okay. Yeah.
To find A, can't you say lambda divided by 4?
Oh yeah. I mean, the other thing as well is that if you knew these lengths, here to here, here to here, here to here, and here to here, they're all the same. So you're right, if you wanted one of those pieces, oh, we need another letter now, what do I call it? Hell, I don't know. Run out of letters. X, okay. X. You're right, Joshua. X would be the wavelength divided by 4. Or you could also say the wavelength is 4 of those. 4 of these pieces here. 1, 2, 3, 4. I mean, there's so many different ways to break it up and to look at it, okay? I'm just giving you some basic ones here. But you're right. You're right. Okay, anything else to ask about this now? No? Okay, so we can go on to motion now. So we're going to talk about frequency and speed. So in my last picture, the wave wasn't moving. Now the wave is going to be moving. So we have our wave and it's moving to the right. So I'll try my very best to draw that for you here, graph it. So let's just do a sin x. Okay, now what I'm going to do for my graph is move this a little bit to the right. So I'm moving it a tiny bit to the right. So let's say oh, maybe that's a little, not too much. All right, and then I move it again. Use your imagination, children. So you can see that the wave is propagating, is the verb you got, moving to the right. Okay? Imagination. So the wave is moving now.
It's the same thing like we learned in maths. So when you add something to x, it moves to the right or left.
Yeah, well, I'm just doing that to make the graph, but I'm not talking too much about that right now. Let me move it a little bit more. So we have sin x, and then we'll do sine, let's say x minus 0.25. Okay, so I'm not even going to try anymore. So it's moving anyways. So whatever speed it's moving at, let me call that speed v for velocity. Just like linear motion, the unit would be meters per second. So the unit here is, it's in meters per second. Okay, so our first definition now is going to be the definition for frequency. Yeah, but try to give it to me in words now, if you know frequency.
Is it
number of oscillations per second.
number of oscillation in 1 second?
Number of cycles.
Yes, yeah. The number of cycles in 1 second. Okay, so what you need to imagine here, in my little diagram, here's someone standing here. This wave is moving to the right. So in other words, this person here counts how many wavelengths go past him. So there's one wavelength. Actually, I'll draw that bigger. Okay. So here is my man standing here, and this wave, you can think of it like an ocean wave, is passing by him. And what you do is you count how many cycles, how many wavelengths go past. So let's imagine this whole wave here goes through in 1 second. So what happens is we have, let's see, up, down, okay, 1, 2, up, down, up, 3, 4, 5. There's 5 wavelengths that will go past him in 1 second. So in this example here, if this happens in 1 second, we say that the frequency is 5. And the unit for frequency? Hertz. Yeah, because if you think of, well, we'll talk about hertz in a moment, but that's the unit, hertz. So 5 means 5 wavelengths have passed them in 1 second. Okay. Now what's great is there's actually a formula to relate, yeah?
So could you define like number of wavelengths per second?
We might need to make it a tad bit more formal, say number of wavelengths passed through a point in 1 second, or number of completed wavelength cycles, or something like that. Just number of wavelengths by itself might not be enough. There has to be some reference to time as well, or point. Okay, so what's nice here is there actually is a formula that can relate all of these variables together. The speed of the wave, its velocity, is equal to its frequency multiply its wavelength. Very, very simple and very, very important formula. So please make good note of that.
So the velocity of wave.
Huh?
So the velocity of a wave.
Yes, yes. Is the wave's frequency multiply the wave's wavelength. And this is so important, some people in some books actually call it the wave equation, or equation of the wave. Yes, I know it's ridiculous, but there you go. Okay. Right. There's a, let's see what I'd like to do. Yes, principal superposition I think I'll do, and then I'll do Snell's. Then interference. Yeah, okay. Right. Can I scroll down now? Yep. Okay, so next, principle of superposition. So you know it's important because it has principle in the title. That's the clue.
And there is a part of the word which says super.
And that also, yes, it has super in it as well. So it is important, okay? And the best way to explain this first is with my graphing program here again. So we have one wave here, let's say it's sine x, and we graph that. And then there's the graph there. And then let's have another wave, much, much smaller though. So let's say 0.1, and let's make it cos x. And we graph that. Maybe that's a little bit too small. Let me zoom in a bit. Okay, there we go. Oh, and you know what? Actually, let me delete that one. Delete that one. Start this one again. Okay, so I'll still do 0.1 cos, but let's make it 10x. Okay. There we go. So what I've got there are two waves, and you can picture them as sound waves. Okay, so the red one, or well, doesn't have to be sound, could be ocean waves, whatever. We have two waves. Now on my graph they're on the same picture, but in your mind, picture them separately. The red wave is here, the blue wave is here, and they're moving. And then what's going to happen is they're going to combine to make a new wave. So I'll just give you a minute. I want you to try and draw roughly what you think the new wave will look like, and then I'll show you here. So the red wave, the blue wave, they come together to make a new wave. I want to see what you draw. So draw this combined wave for me. Huh?
Can I use two
Are
ocean
they going
waves?
opposite sides?
No, combine the red and the blue. They're coming together. What's wrong?
Nothing.
Yeah, I mean-
How do you think it will look like?
Fine, have you drawn it?
No, I don't think it.
Fine, okay, but you will draw it, right?
I don't know how it will look.
No idea?
Still, can I use two ocean waves instead?
This, whatever way you like. I really hope this belongs to Dan more soon, or otherwise I have serious questions about someone else in this class. Top model, anybody? No?
It was here before here.
Okay,
Sure.
good, good. Otherwise I'd be concerned about someone. Okay, have you got this drawn? No? No? No imagination?
No, is it like this? Pointy-ish?
No? Alright. Huh? No?
Is it
No.
gonna be?
It should be slightly compared. It should be in between the bigger.
Yes, draw. Show me.
Is it gonna be like those of?
Look, those biology students downstairs, they draw all the time. I ask you to draw one thing for me, come on.
Is it gonna be like those earthquake magnitude ones?
Just draw it for me.
What? Like this?
Not quite. Maybe this is why we're not in biology, is it?
Yeah.
Okay. So let's have a look at the graph now. So this explains exactly what I mean by principle of superposition. The principle is this. If I have two waves and I want the combined wave is just mathematically the same thing as adding the two waves together. So wave A and wave B, and I want to combine them together, it's actually just A plus B. So that would mean here, 1 plus 2, wave 1 plus wave 2, you see there's the formula there.
Yeah.
So imagine for the first wave you had a formula for its graph, the second wave you had a formula for its graph, the total is actually just the two formulas added together. And if I draw this now, okay, are you ready? Yes? That's it there.
Oh.
Yeah. No one was even close.
Yes, I know.
No, he was.
Close. Okay. Compared to everyone else, yes. So can you draw it the correct one now, please?
Let's do this.
Yes? Now this is the computer. The graph is perfect.
Do I have to draw them like in the same?
No. You can draw them separately.
Do that. It's the dark white. It's straight line with the very first letter. How do you see? Wait.
Did you draw it now?
Yes.
Yep. Okay. So just one more of like this. So let's do a little bit of an easier one together. So if you look here at sin x and cos x, okay? At the beginning, what is the value for sine x, the red one? It's 0.
0.
And what's cos x?
1.
1. So the sine starts low and the cos starts high. If you put them together, it will start at 1 because you'll have a 1 and a 0. Now let's look at what happens. The cos will, the sine will increase and the cos will decrease. So what I'm picturing is the wave will start at 1 and it might even stay kind of roughly at 1. But later, let's say down to here, the cos is 0 and now the sine is 1. So it's not going to be quite always 1, but it's always trying to be near 1. So when I draw this graph, let's see what we get. Graph it. So here it starts at 1, then goes a little bit past 1 up to 1.5, and then drops back to 1, and then down to 0.5. So for a lot of the journey it's hanging around 1, but then of course it'll have to go negative later in the graph. But you can see the black one is the red one and the blue one added together. And the way to add them is just by using algebra. This is called the principle of superposition. So we'll try and write that down. Do you need?
No.
Not yet. So when two waves combine to form a new wave, then the new wave will be the algebraic sum of the two combining waves. Or in other words, if this is the formula for the first wave, and then this is the formula for the second wave, then the combined wave, it will just be the two formulas added together. Simple, useful, important result. Principle of superposition.
Well, what if we don't know the graphical formula side by side? How do we do this?
Often we don't. And what's really important here is just the idea that if you have a wave at a crest that combines with a wave at a trough, then the two waves might even cancel. Or a crest meets a crest to make an even bigger crest. That's really the key ideas we're to take from this. So if you have a crest and a crest and they meet, they'll form a bigger crest. If you have a crest and the trough, they cancel. Yeah. Which is the vocabulary we're going to do next. Okay, you're still writing that. Did you write that down, Joshua? Yep.
Wouldn't it be minus f2x?
Huh?
Wouldn't it be minus f2x?
No, plus.
Sorry?
Plus is right. Yeah. Okay, so a little bit more vocabulary when it comes to combining waves. So we're going to talk about... you're still writing, okay, hurry up. Okay. So I'll go down here. Yes? Mo, you got it there? Yes. Are you sure? Okay. So coherent. Whoops. coherent. So we say two waves are coherent if they have the same frequency. By the way, we've actually done frequency before in the mechanics section, and we have a formula for frequency. Does anyone remember it? 1 over T. So, and maybe it's just worth reminding people of that, that if you do 1 over frequency, that's the time for one cycle. Okay. Anyways, coherent means the waves have the same frequency. That's a special type of combination, when the waves have the same frequency. So, in my example here in this graph, all these waves have the same frequency because they all have B in maths class. B is 1. See that? So they all have the same frequency. When that happens, something special could happen. So have a look at this one. First wave, graph it. Graph it. And then second wave, graph it. Looks the same, doesn't it? Now let's add them together and we'll get this wave. So in this example here, the two waves have the same frequency, but what's even better is that they exactly match up. So the maximum matches the maximum in each wave, and the minimum matches the minimum in each wave. When this happens, they combine perfectly to make a much bigger wave. This is actually called, has a name. Does anyone know that? No? Think of English now. What word means to build something?
Construct.
Construct, yeah. So, yeah, this is called constructive interference or constructive combination. Constructive. Described as constructive.
Basically, when two waves build upon each other, they become larger waves.
Yeah, that's called constructive. Constructive, like construct.
So which one's progressive?
Progressive, I think, is another word just for longitudinal. Yeah. So you might be thinking, oh, okay, so we can have constructive combination. So could we have the opposite? Could the waves cancel each other? Yeah, and that would be called destructive. And you can have destructive. Destructive will look like this. So we have sine x.
Minus sine.
Yeah, very good. Minus sine x. So there's the first wave. Graph it. And there's the second wave. Graph it. And now, of course, add them together. 1 plus 2. Graph that. And you can't even see it. There, they're changing the colours in the middle there.
So the waves
Flat. So what do we call this? How could we describe this? As destructive. Not only is it destructive, we can say it's completely destructive. It has completely destroyed the wave. The two waves have come together and have completely destroyed each other. Destructive. This actually has an important application. Does anyone know where destroying waves could be useful? True, but no.
destroying waves.
Yeah.
Created.
Oh, good. To stop the resonance, maybe. Yeah. That could be one, but there's actually another one.
Glasses.
Now, I'll give you an example, okay? I'm talking, you can hear my sound wave coming out.
Theatres. When they
Uh,
have this.
Soundproof. Is that
Soundproofing is what we're going to talk about, yeah. Now, think about this. You can hear my sound wave, and the people at the back will not hear it as loud as the people at the front. Of course, you know that. So, when you look at a plane, you can see it's very, very, very far away, but you can hear it.
Yeah.
So that means it must be really loud, and in fact it is really, really loud, that if you were beside it, like it could make you deaf. But of course you all flew on the plane to get here. So you were inside the plane, which is much closer to the engine than here we are on the ground. But you can't hear the engine as loudly. The same goes for people who work in a factory or people who work in a mine. It's very loud machinery, but it's not so loud as you might think when you're inside it. And that is because of this. What happens is, when the sound wave comes out of the machine, like the airplane, there'll be another machine that makes another sound wave. And it'll make the same wave except flipped upside down. So that when it combines with the machine sound wave, it cancels. Like a positive and negative one.
So that's noise pollution.
The way to cancel it. But you might think, why is it not perfect? Why do you still hear the engine when you're on the plane? And that's because what's happening is the machine is trying to mimic or make the same sound as the engine. But of course, the sound of an engine isn't perfectly repeating itself, isn't it? Like, you know, it changes slightly. It's not a continuous, perfect sound. So that means the machine will never perfectly cancel the engine sound. It'll never quite match it up. And this is a good example of destructive combination then. Okay? You know, you have something similar with, I think they had the similar idea of the American military helicopters in one movie, like the silent ones. So you don't hear the helicopter coming down. And I mean, you might think that's a ridiculous idea, but it's not too ridiculous, because all you would need to do is make the same sound as the rollerblade, except, as you said, Mo, just have it upside down then. Okay? So, simple but useful. Important application.
Well, you have read some of those silent rooms that they make in universities. It's a whole room that absorbs all the wavelengths.
Yeah, but that's different to this. It's not cancelling anything. It's just not letting anything in or out to begin with then. Okay, so I want you to write those two words down. Constructive and destructive.
So besides same frequency, coherent wave has same wavelength as well.
Does it need to have the same wavelength?
Yeah, only then they can have the same frequency. I mean the characteristic of coherent.
True! Or actually, I think we can even relax that a little bit and just say one wavelength has to be a multiple of the other wavelength. No, I don't even know if it has to have the same wavelength.
I mean, what if the question asks what's the characteristic of coherent wave? Two characteristics.
Of coherent?
Yeah. Same frequency.
I think sometimes it might have to be the same amplitude. Let me just double check that for you. Coherent sources have a constant phase difference, which means they must have the same frequency, and for complete cancellation to occur, the amplitude of the superposing waves they produce must be about equal. If their phase difference is not constant, at a certain point they may be okay, so it looks like coherent just means the same frequency, but that's not enough, as you're saying, to get cancellation. So for the waves to cancel, they must be the same frequency. But what else must be true?
Speed.
Same amplitude. Yes. What else must be true?
Same speed.
Yeah, well, same frequency we said at the start. Same frequency, yes. Same amplitude? Yes.
And wavelength.
Does the wavelength need to be the same? Yeah, okay, same wavelength. But something else I think much more important.
Speed.
No?
Direction.
Well, direction, yeah, more important than that. When you match them up, a maximum on the first wave must match with a no for these, yeah, minimum on the second wave. Okay, that's, I would say, the key part. Yeah. So yes, same frequency, same amplitude, same wavelength, and max with a min and min with a max, they cancel. And for constructive, max with max and min with a min. And that's for completely constructive. You know, that's for maximum combination. You know those lasers that you might have in your computer that burn the CD. They use constructive waves to do that. Because what happens is you have some red light, and then you have another red light, but with the same frequency, just like in my last example. So what happens when the waves add together? They get bigger, don't they?
Yes.
Yeah. So all this laser is just lots and lots and lots and lots and lots of red light, but all perfectly the same, and they all perfectly add together to make this really intense red light that burns the CD. So we've seen an application of constructive and destructive. You need to know that because for the exam it could say for 1 mark what is an application of constructive waves or what is an application of destructive waves. So please write my 2 examples down. Okay? So constructive is when you want to make bigger waves, to make more energy, to maybe burn something like a CD. And destructive is when you want to cancel waves to maybe reduce noise, like in an airplane. Okay, so just another piece of vocabulary there. Interference is really just a verb. It means waves that add together. But normally we always talk about adding together of waves which are coherent. Maybe I can try and find an animation. If I have an animation here, this would be great. I mean, the book's good, but it's much better to see this as a video. So I'm going to show you an example of interference. 2 waves coming together to add.
Do you know this website where they have lots of Java programs?
Do you know what?
Physics experiments?
Oh, I don't necessarily know its name, but I might have seen it before.
Do you know what is it? What website?
I forgot the name.
I do remember seeing, though, on Wikipedia, a little animated GIF of coherent waves coming together and adding up.
I'll find it, I can send you the link to the website.
Yeah, that'd be nice. So it has a little animation of the
They have
waves.
Java programs with different experiments or just animation.
Yeah, okay, that sounds good. They might have like a pendulum or something.
Yeah, they have, I think they have everything.
ET or something. Is it the PHET?
Yeah. PHET, that's code.uk, I guess.
Interference. Here we go.
Yeah.
Yes. Yes. I want a little animated. Oh, this looks like it could be it. No. Oh, come on, you had it here when I saw it last time.
Oh, sir,
Yes?
you could check PHET simulation. That's the one. Yeah, exactly. That's the one.
Or you can like Google interference physics and then check on images that probably find.
No, I'll get it later before the end of the class. But,
So it's PHET
oh
simulation.
yeah, I'll get it later, it's
Just
okay.
have a break and you can.
Yeah, it's
No.
Different
That's the
I
website.
think you break your past 9.
Yes, 2 hours.
Really?
Yeah.
And did you have a breakdown?
No,
I was going to say that.
she never gives it away.
Alright. Wait. Really now, just 5 minutes, okay?
Thank you.
And yes, I'll go find a nice animation then.
PHET, that
PHET.
The first one is experiment.
Email me the link, Tanish, and I'll just. Or do you have it there to show me?
You could just go to Google and just
Just
type
say, no, I-
PhD simulation. That's all.
Okay, nice. I'll see what I can find. Now,
It was there, so.
you can close it after him. The website, when I click the link, is not running the animation, so I'll just have to look at it later. And come on, and I feel using Google Images is just too risky in a classroom situation without checking the results first.
It's waiting.
It's too risky, and I don't want to do it. So I won't use Google Images, and I'll just try and look at the program later. But I'll try my best to draw it. Okay. So firstly,
You never know.
yes, you can never know. All right. Firstly, if we have a wave that's passing through what's called a slit or a gap, it's called a slit or it's called a gap. So here's our wave coming in, like this, and then what will happen is it will spread out like this. And in fact, the smaller the gap, the more it spreads out. So if I had this situation, a smaller gap, the wave will actually spread out at a bigger angle, whereas here is a smaller angle. So if you take it to the extreme, if you had a really small gap here and you had the wave coming in, it would spread out a whole lot then. This process is called diffraction. That's what diffraction is, yes?
Sorry, do waves move at the speed of light?
No, just light waves move at the speed of light. Sound waves and every other waves don't. Yeah, which is actually a light wave as well. Okay, so that's diffraction. So diffraction, if you want to write the definition down, how would you describe this in a sentence? Yeah, the spreading of a wave as it passes through a gap or a slit.
Can you repeat that?
Yeah, well, I'll write it down. What are you saying, Joshua? Spreading is a bit more technically accurate. Diffraction is the spreading out of a wave as it passes. Yeah, okay. No, we're getting very technical. I like technical, but I also like to try and keep it as simple as I can. So I'll just say passes through a slit. And a slit is just a gap. Yes, Tanish?
Oh no.
Focus now. Okay, can I scroll down?
Yeah.
Okay. You have that?
Yeah.
No, and Dana. I'll wait a moment. Okay. Now, this diffraction can be useful for the next definition. Okay. So here we have this situation. Okay, so here is our first wave. It comes in here and it spreads out. So maybe actually draw that again. The effect of this one here is just to spread it out so that it hits here and then it hits here. So I'll draw this in red. Now just to make it clear, this is a longitudinal wave. It's the one that's vibrating back and forth. Okay? Oh well, actually, no, you could think of it also as a transverse wave. Actually, no, sorry, let's think of it as a transverse wave. So it's like an ocean wave going up and down as it moves out.
The line represents crest.
Yeah, well, that's what I'm going to say, that for my diagram, when I draw the line, it means the crest, the maximum, okay? So we have this wave, look, and it's going up and down, up and down, up and down, up and down. And each line that I draw on the screen, that's when it's at the top. Okay, so that's the red one there. And then I'll draw the second one underneath it in a different colour. Okay, in yellow. Now, yes, I said where I draw my lines, that is a maximum. So using our vocabulary, what happens here when the two waves meet? They make a new wave, don't they? And by principle of superposition, it means that the new wave will be the first wave plus the second wave, right? And if they're both maximums, the new wave that's produced is constructive, so it's really, really big. But in the middle of the two maximums, so I'll draw that here in a dotted red, this here would be minimum, wouldn't it? Yeah. And what would happen, do you think, when this minimum meets this maximum?
Cancel.
They cancel. So you have a cancellation here.
Sorry, those gaps in the place of two of them, they're the same, right?
What do you mean, the same length?
Those gaps here.
Yeah?
They're the same.
Oh, they're the same, yeah. So when this maximum meets, when this minimum meets this maximum, it makes here no wave. Okay, and then what about when this maximum here meets this maximum? You have a wave. So the point I'm trying to make here is sometimes the waves come together and add, and sometimes they come together and they cancel. But if you look at this, let's put a screen here. If you picture, this is why I said an animation would be good. If you picture this is moving along here, when it hits the screen, what's hitting the screen? This maximum. Maximum plus maximum, really big, black dot, hits the screen, makes a really big impact. But what about when this white one hits the screen? Well, nothing will happen because there's nothing here. What will happen on the screen is, in the center, you'll get this really, really big impact point. Then there'll be nothing. And then you'll get another point where they impact. But this one's not as big. And then you get another point. And again, it's getting smaller. Because as this moves out here, the wave is getting smaller. So what I'm saying is, the picture that you make on the screen, if this was light waves, will be lots of red dots and lots of no dots. So if I was to look at this piece of paper, if it was light, it would look like this. So if I take this piece of paper now, you'd have a really bright dot in the middle. That's this one here. I'll call it 0. And then beside it, you'll have bright dots, but they're not as bright. And that's called 1. And that's called 1. And then here is 2. And then here is 2. And then the next one is another dot, but again, it's not so bright. And the reason that there's no light here is because this is where they cancel. 0.
I think that there should be YouTube videos of that.
Oh, there definitely will. Oh, yes, yes,
Just
yes.
your basic animation.
Yes, there definitely will be videos. And again, I don't want to risk searching for videos right now. Just too risky in a classroom. But what you got here is light in certain parts of the paper. Now, you really need to think about how important that is. That light there and that light there, they combine and they make everything in the room brighter. But the way I put the paper together means when the two lights combine, when they hit the page, some areas will be bright and some areas will be dark. And this is because of constructive and destructive interference. Okay? So this is an important and simple experiment showing constructive and destructive interference. And does anyone know the name of this experiment that I drew? Where you have light, paper, and then paper again with 2 gaps, and then a screen at the end of the room. Not Snell's, Young's.
Young's double
Young.
slit experiment.
Yes, this is Young's double slit experiment. Very simple to do. Okay, how would you do that? So what would happen is on a really sunny day, you would, let me show you here. Can you look? On a really sunny day, you would pull this blind down, okay, and just have a little hole in it, so a little light coming through. And of course, you cover the window up and turn the lights off so it's dark. So you pull this down, and then what you do is you put a little hole in it. Then you get one piece of card here in front of the hole, but have a slit down the middle. And then you have another piece of card later, and it has 2 slits. And then one light comes in, spreads out, goes through the 2 slits, and then when the light combines again, sometimes it will add and sometimes it will not add, it will cancel. And then the light comes out from the card here, and then you look at this wall, and you have a bright circle in the middle. 2 more circles, not as bright. 2 more circles, not as bright, etc. And then of course, if you take the cards away, how many circles? Just 1 from the window. But then you put the cards up, and it splits it into all these circles. That's Young's double slit experiment. Very important for the exam. So important that it will get its own lesson. So we'll have its own lesson on it. But I just wanted to introduce the idea of Young's double slit experiment in this lesson. Okay? So write that down. Young, as in old. Young's double slit experiment. That's what this is called. Young's double slit experiment. Trying to see if it's even in the. Does anybody know the name given to those circles that would appear on the page, on the wall?
Spectrum.
I was thinking a different word. I know we're saying spectrum, but that's actually for something else. Does anyone know? Begins with an F?
Focus.
Not focus? Yes? I thought I heard it. Fringe, very good, yeah. It's called fringe pattern. Yeah. Fringe. So fringe pattern or fringe image or fringe picture. Write that word down. It's important. Okay.
Will we be studying about Young double slit experiment?
Maybe not the next class, but we will do it. Okay. So that's Young's double slit. We will come back to this. It gets its own lesson, it deserves its own lesson, and it's really popular exam question. They like asking this one. The reason it's so popular in the exam is because there are not many wave equations or wave questions, so they don't have much of a choice. So Young's double slit is one of them. What I do want to spend time on now is the other important formula or result is Snell's law. Does anybody know Snell? Have you heard of it yet? Snell's law. Okay. Right, so first thing here, we have two different materials. For example, this one here could be like air, and this one here could be like water. And what's happening here, when light passes from air to water, it doesn't travel in a straight line. The angle changes. Yes, you get a different angle. So, I mean, it doesn't have to be air and water. It could be like glass and water, glass and plastic. Two different densities. Yeah, two different mediums, two different materials. So here is, we call it material 1. Here is material 2. This line here is called the normal. Here is the first wave, and it hits here, and we'll call this angle I. And then it changes into a different angle, and we call this angle that it changes R. This might be looking familiar to some people. Yeah. So there actually is a relationship between the two formulas.
Is this refraction?
Very good, yeah.
Is it Snell's?
It's Snell's law, yeah.
Sine over...
Yeah, it turns out that sine I over sine R, in fact, is a constant. So for example, if I do this experiment and measure I and R, and then I change the angle for I, so what you imagine here is I have a little light box, shoots out a little laser. If I was to change this here, so it's a different I, so it would be a different R. I'm not drawing this great, I'm sorry, but it's a different I and it's a different R. If you calculate sine I over sine R again, you still get the same answer, the same constant. So this is called Snell's law, the most simplest form of Snell's law.
What's the letter for this part?
Oh, well, I'm going to do that in a moment, yes. And why does this happen? And the reason that this happens is that the velocity of the wave is changing. Okay? And the best example I can give you, if you try to picture this, is if you have a car that's driving on a dry road. So it's driving on a dry road, and then it goes onto, let's say, mud or ice or something. It will not continue in a straight line. It'll change a little bit. Okay. Of course it won't continue in a straight line. Unless you manage to go perfectly straight. Okay? But I mean, if I try and look at here at the board, here's the car, here's the dry road, and here's the wet road. So if it goes straight, then it goes straight. That's fine. But there's something interesting happens if it goes at an angle. Okay. Now with the car, we can think of it about as wheels. So when the car goes at an angle, these wheels are different on a different material than these wheels at the back. Yes. Now if the road is wet, what will happen with the wheel? The wheel might spin and not grip the road as much. So will the car go faster or slower on the wet road? No, slower, because the wheel is spinning and it's not getting the ground. It's like skidding. You know this verb, skid? So this is going slower and then this is going faster. So of course that means the car, it's like someone is pushing it from the back. because it has more speed from the back, more force from the back. So this will cause the car to then change its angle. Now, of course, my example is only a real life example to try and get you thinking about this. This has nothing to do with light, because light doesn't have wheels, okay? But it's still the similar idea, that when the light passes from one material to another, it doesn't travel at the same speed in the new material. This causes an angle change. This is called Snell's law. And in fact, that constant is actually related to the two velocities. And I'll give it to you now. So if we say in the first material, it's going with velocity v1, and in the second material, it's going with velocity v2, believe it or not, this constant here is actually just v1 over v2. This is called sine I, sine or, is v1 over v2. Kind of simple. But there's something else that could equal as well, which I'm going to look at now in a moment.
Density.
It's kind of like related to density. Yes, you think you might know the word. Yeah. Refractive index. That's it, yes, refractive index. That's what I'm going to look at now. That formula is important. Yes, N. I'm going to go to the side now. Okay, so let's take something here like air, and then let's take something like glass, and then let's take something like water, and we could have a sound wave. So here's your sound wave, and then it hits the air. Well, it was already in the air. If this was a speaker, maybe computer speaker. Okay. And we have our sound wave, and then it hits the glass. And then we have our water wave, our sound wave, and then it hits the water. This is V1, V1, V1. All these velocities, V2, will be different. Some materials are better for sound to travel in than other materials. Of the three materials, which one is the best for sound? I think water actually, yes? Water is, yeah.
Especially the surface of the water.
Yes, but glass is not too good, I don't think, for the traveling of sound.
What the name in glass?
Huh?
Should the water, air, and glass?
Yeah, I think water, air, and glass would be the correct order.
Water, not air.
Check it.
I think the molecules in the water, it's much easier for sound to travel through it by using the molecules.
For any wave.
For any wave, it's true, not just sound. Yeah.
Take the dolphins or
Yes, the thing about air is it's not that close together. The molecules are quite spread out, you know. I mean, you'd be surprised that there's not much difference between air and a vacuum.
Yeah.
But when you're in water, you definitely have all the molecules around you. You can feel them. Anyways, the sound will change its velocity in different materials. So some materials are better than others for allowing waves to travel through them. So we need a way to measure how good the material is for allowing the traveling of waves. And that is called the refractive index. Refractive index. This is what you do. You take your material, so glass, air, water, whatever. You take something that has a universal speed. So that would be a light wave. And it goes in. What's the speed of light? What letter do we use? What letter do we use? C. And what is C? It's about 3
times 10 to the power of 6 meters per second.
Yeah. Like roughly 3. I think it's like 2.99.
Yeah, so it's originally 2.9, but
it's 3, yeah. So what happens here is the light goes into the material and changes its velocity. When light when light passes through a material, it will always go slower, unless maybe it's a vacuum, empty space, and then it's the same speed. But you can never make it go faster. It'll always go slower, always, without exception. So what you do here is you make up a term called refractive index n, which equals C over V. Now, I just said it'll always go slower. So which is bigger, the C or the V?
C.
The C. So we have a big number over a small number. So this will always be more than 1. And when would it equal 1?
When the C's
Vacuum.
Well, that's the same in the vacuum, okay?
So
Yes.
is this connected to the Snell's law?
It is.
Yeah, this is the constant, right? No.
We're getting there, yes, we're getting there. So, when people talk about how good materials are for allowing light to pass through it, they talk about refractive index. So what do you think? The bigger the refractive index, the better or the worse?
The better.
I'm
Sorry.
I know, the worse. Because if you had a refractive index of 1, what would that mean?
Best.
Perfect vacuum, the light just continues as light speed. But if you had a really, really big refractive index, it means the light really slows down, or the wave really slows down when it passes through. So in other words, the bigger the better, the smaller the worse. The wave really feels resistance, so to speak, as it tries to move through the material. Okay?
It will like 0 point something.
No, impossible. Impossible. It must be at least 1.
It can be bigger than speed of light.
Yes.
Yeah. Speed of the-
Yeah, so it must be at least 1. Okay? But of course it can't really be 1 because then you have a vacuum, and that's not a question. So it's always more than 1. Now we tie this back to Snell's law. So if we go back to Snell's law now, back to Snell's law, this material will have a refractive index. This material will have a refractive index. For example, if this was a vacuum, it would be 1. And if this was water, I believe it's roughly 1.33. For example, okay? If I go down here, we know that N equals C over V. So that means V equals C over N. So this here would be C over N1 over C over N2. The C's cancel and you're left with N2 over N1. So that's another way to write Snell's law. So you have 3 ways to write Snell's law. Sine I over sine R is some constant. Sine I over sine R is equal to V1 over V2. Or you could say sine I equals sine R equals N2 over N1.
Or N1 sine I equals to N2 sine.
Sure, you can rewrite this as many ways as you like. These are the 3 main ways.
This is all just defined.
And which one you use depends on what they give you. So for example, if they say a light moves from this material with refractive index N1, then of course you know, oh, well, I'll have to use the last form. But if they say a sound wave moves with this speed to this material with this speed now, then of course you'd have to use the second one. And for your first experiment, which, now this is your first lab you'll do in January, your first lab is Snell's law. And I just want you to use the first formula for Snell's law here. So what you'll get is, I'll give you a tank of water, and it'll have a little laser at the top. You can move the laser around, and you can measure the I, and then you can measure the OR, and then you have to make a table and see if the sine I divided by the sine R is a constant.
So we're doing here.
Yes.
Here.
Yes. I have all the equipment in the teacher's room. And well, I think I told you this before, but my equipment is laser, the water tank, for measuring the angles, okay?
Yeah,
We have an ohmmeter, an ammeter, a battery, a resistor, a switch, a variable resistor, 2 cars, little speedometers to measure the speed, weights, trolleys, and of course you also have one of the equipment,
Yeah.
the most expensive one, the pendulum. Of all those equipment, the most expensive thing is the box of weights for Newton's law. It's like €100 for the box of weights.
It's too much.
Yes. The water tank was maybe €25.
How big is it?
It's only going to be about that big. So you slide the laser on the top. Does the job well though. Yeah. Yes, well this is the thing, the nice thing about what happened is with the previous physics teacher, they took all the students to DIT to do the labs, like the biology and the chemistry students. But I feel like it would be more fun if we did it in the classroom.
Yes.
And the thing is, I think it's less scary for the students because it's more of a controlled situation. Okay? Whereas you go to DIT and there's the lab technician,
And then it's like,
here's the equipment, good luck.
They're always walking like, don't touch these.
Yes, yes.
Don't turn on this computer.
Yes, I will take that role on in the classroom then. But fortunately, there's not lots of expensive equipment around for each person. Okay? So there's Snell's law, and your first lab will be about Snell's law. So let's have a look at an example question. So if we go to the questions at the back.
You have 4 minutes.
Yeah, I just want to do the Snell's law example. Let's see. Snell's law. Actually, the first question is Snell's law. So if you look at question 1, what I'll do actually is I'll let you try it first and then I'll do it. So let's just read it together. Well, the first part we don't have to do. State Snell's law. So I'll just say it. Snell's law is that sine I divided by sine or is a constant. Oh, by the way, I didn't say this. I and or, there's a reason I choose I and or, because there's a word in English that means going in and coming out for light. I for incidence and or refracted.
Yes.
Yeah. Or just I and or. Anyways, light travels through a pool of water, a tank of water, and its speed is 2.2 times 10 to the 7th centimeters per second.
2.2 times 10 to the 7.
Sorry, 2.2 times 10 to the 10 centimeters a second. Calculate the angle the beam can make if the light then leaves at 3 times 10 to the 10 centimeters per second. So the first part is calculate the angle. So if you look here, what they're saying is the light goes from the air to the water, and they give you the speed here and the speed later, and they want the angle it makes.
The second speed as well?
It says there 3 times 10 to the 10.
Can we leave it in centimeters?
You can actually, because the units will cancel, so that's fine.
Actually, once again, it's kind of 1%. The first angle is 90, right?
The first angle is 90, not 0. What the heck is this person?
Second angle is
Yeah, just be careful when the water heads straight in. Remember, I don't have it drawn anymore. Oh, battery low. Oh, I left.